IOPS is an acronym for Input-Output Operations per Second, and it's pretty useful at measuring random workloads. But, and I can't stress the following enough, IOPS numbers are absolutely useless without associated latency figures. Also, IOPS literally come in all shapes, sizes and types. So just as IOPS is useless without latency figures attached to it, it's also not much use without detail regarding the type of I/O. Read-write, big, small, and random or sequential. For example, an array will almost certainly perform a lot better at large block sequential read I/O than it will at small block random read, especially if the array is based on spinning disks, obviously due to the mechanical latency involved with random workloads. All the head movement and the rotational latency and the likes. On the topic of IOPS, it's important to know that the capacity of a drive can affect its performance. For example, a 1 TB drive that can do 100 IOPS may not perform as well as a 4 TB drive that can also perform 100 IOPS. The reason for this is that the 4 TB drive can potentially store up to 4 times as much data as the 1 TB drive, and therefore potentially be subject to 4 times as much demand for I/O. As an example, if you could store a database on your 1 TB drive, you might be able to store 4 databases on the 4 TB drive. But that's just from a capacity perspective. You have 4 times as much capacity, but you don't have 4 times as much performance or 4 times as many IOPS. So you need to keep this in mind. IOPS per terabyte is a way of measuring this. Our 1 TB drive has 100 IOPS per terabyte, but our 4 TB drive only has 25 IOPS per terabyte. Also, IOPS can have quite an impact on CPU load for both the storage array and the host that's issuing the IOs. For example, a workload of 1000 4K IOPS will be a lot more computationally intensive than a workload of 100 40K IOPS, even though they're both processing 4000K. That's because each I/O has to be handled individually, placing a higher load on the CPU. And when the CPU load gets high, performance tends to suffer. It's usually a good idea to try and keep CPU load below 70% on most storage arrays. But that's only a general guideline. The important things are: 1. To understand that lots of small I/O can dramatically increase CPU load, and 2. To monitor CPU load and try and keep it low. Anyway, another metric associated with performance, but more geared towards sequential or streaming workloads, is megabytes per second. As the name suggests, megabytes per second refers to the number of megabytes a system, or maybe a single drive, can transfer in a second. So higher numbers are better. A system that can sustain 1000 megabytes a second is capable of more throughput than a system that can only sustain 500 megabytes a second. However, 2 things to note. First up, megabytes a second numbers for read and write will usually be different. For example, all flash-based systems might be capable of something like 1000 megabytes a second write, but 5000 megabytes a second read. Second up, unlike with IOPS, latency just isn't as important when it comes to measuring throughput in sequential workloads. And finally, on IOPS and megabytes a second, just about all real-world workloads will be a massive mix of everything you can imagine. Small block, large block, read-write, random and sequential, making everything really appear random. And on that note, let's talk quickly about random versus sequential workloads.